Hi, friends. In today's lecture of the hydraulics and hydraulic machinery, wherein we are discussing about the critical flow, of course, the specific energy principles. We do devote this lecture to discuss on channel transitions related problems. In the previous lecture, we discussed more on what is a channel transition and what type of transitions are provided in open channels. There are two types of transitions that are provided in open channels. One is one uniform channel, and the other uniform channel of same section will be connected by a transition wherein reduction in width of the channel is involved. So transition is one is reduction in width of the channel. The second transition is to raise the floor of the channel, raising the floor of the channel. And that is what is called as providing a hump. So there are two types of channel transition. One is the reduction in width of the channel. The other one is rise in the floor, which is called as the hump. So related to it, in today's class, we will solve some problems. Channel transitions. Number one is reduction in width of channel. That means if I take it in plan, suppose this is a channel which is connected to another channel. So the channel width here is B1, here is B2. This reduction, it is in plan. This is what we call it as reduction in width of the channel. So second one is channel with raised floor. That is, if you take the section, so this is section I am drawing, right? This is the channel floor. Here a hump is kept. That means the floor is raised at this point. This is what we call it as hump. So these are called as channel transition. This is the water level. This is how the water levels will be. So these are two are called as transitions. Why we provide the channel transitions? What are the functions actually? The functions may be any one of these or multiple of this. Number one is flow measurement. This is called as metering of flow. This is the main purpose. The second one may be dissipation of energy. The third one may be basically reduction or increase of velocity. We whatever we want, if we want to achieve it, this is the only way. And the fourth one is to achieve critical flow. And finally, to change the channel alignment with minimum dissipation of energy. So under these circumstances, for these to achieve these functions, we provide different channel transitions. So now I will take you to problems. Problem one, I take you straight away. In the first thing, I will take actually a channel with a raised floor. So this is a hump problem. Hump means channel with a raised floor. A wide rectangular channel carries a flow of 2.76 meter cube per second per meter width. The depth of flow is 1.524 meters. Calculate the minimum rise of floor at a section required to produce. This is the purpose. Critical flow conditions. The second one is what is the corresponding fall in water surface. So this is the problem. So if I look into it, what is given in the problem, if you see it, number one, the given data is discharge in meter cube per second per meter width. That means it is Q. It is Q is given as 2.76 meter cube per second per meter width. That's what he has given. So that's why I have written it as small q, right? Then he asked what is the floor rise? Y also he has given. Y is equal to 1.24 meters. That is the depth of flow. His question is calculate the minimum rise of the floor at a section required to produce the critical flow conditions. For example, I choose like this. If suppose this is the channel bed and this is the hump. So this is the hump, right? Now, for example, this is the water surface. This is what? Water surface, right? How this is straight. This is energy line. And this is water surface. Right? Suppose I take a section here. I call it as 1. I take another section here. Section 2. Here the depth is y1. Right? Here the depth he asked it as critical depth. So this is critical depth. Then he asked, what is this? This is the question. Then this is nothing but V1 squared by 2G. Then actually here this is Vc square by 2G. So this is the basic thing. So y1 plus v1 squared by 2g, which is a horizontal datum. Here this is that if I don't know anything, I will call it as delta z. So hump height, if I call it as delta z plus yc plus vc squared by 2g. So this is the general equation. The general energy equation, if you write it, the general energy equation, if I put it, which is applicable in any problem. So at section 1, it is y1 plus v1 squared by 2g. This is at section 1 is equal to delta z here c plus yc plus vc square by 2g. This is the first equation. For any problem of hump, you write this first. Then next what? So y1 is given, right? You can find v1 squared by 2g also, not a big issue, because small q is known, y1 is known. Yc, we don't know. Delta z, we don't know. Vc squared by t 2g, we don't know, unless this side is determined. So at least this and this are determined. You cannot find this, because this is what we need to find. So this should be found out, this should be found out. Only yc is found out, then you know vc squared by 2g is nothing but half of yc. So if this is found, total problem is solved. So how to find next is how to find yc. This is the question. So how to find YC? We know that for critical flow, because they mentioned at that place it is critical flow, right? YC is equal to Q square by G whole to the power of 1 by 3. So it is nothing but actually 2.76 whole square by G is 9.81 whole to the power of 1 by 3. Therefore, calculate 2.76. So therefore, YC, if I calculate, actually, it is equal to 0.919 meters. This is first. Further, you know, for critical flow, Vc square by 2g is equal to half of Yc by 2. Therefore, it is 0.919 by 2, which is equal to 0.460. So two things are over. So let us move now. Now the equation we will see. What is y1? Y1 is equal to, in the problem he has given, 1.524 meters. What is how to calculate v1 squared by 2g? So v1 is equal to what? V1, what can I do? V1 is equal to, basically it is q by y1, right? Q is 2.76 divided by 1.524. So that is equal to 1.811 meters per second. So therefore, V1 squared by 2G is equal to 1.811 square divided by 2 into 9.81. So it is 0.167 meters. So this is also obtained. So Y1 is known. V1 squared by 2g is known. So let us take the equation, substitute in the energy equation. In energy equation written above. So what that y1 plus v1 squared by 2g is equal to delta z plus yc plus vc squared by 2g. So if I put 1.524 plus 0.167, this is on left hand side. Delta Z is unknown. This is 0.961 plus Vc squared by 2g is 0.460. Therefore, delta Z is equal to how much actually? 0.312 meters. This is the answer. Once this is obtained, the next bit B is what he asked. change in water surface elevation. So if you see in the figure, actually the water surface is like this, and this is the energy line. So this is V1 squared by 2g. This is Vc squared by 2g. This is water. So therefore, it is nothing but actually Vc squared by 2g minus V1 squared by 2g. So if I take it like this, then this is Vc squared by 2g is 0.460. V1 squared by 2g, I got it already 0.167. So if I subtract it, then I will get 0.293. That's all the answer. Very simple. So the what is the crux of the problem here? Energy equation writing is one. That is one problem. The second crux is what? YC equation. That's all in this problem. So let us take the second problem. In the second problem, what I will take it is only the reduction in width. Reduction in width of channel. Another transition I will take it. So if I take it, a rectangular channel is 2.5 meters wide and carries a flow of 2.75 meter cube per second at a depth of 0.9 meters. A contraction of the channel a contraction of the channel width is proposed at a certain section. Given in figure. Find the smallest allowable contracted width that will not affect the upstream flow conditions. So this is again second type of problem. I will take it. So first thing is how the section will be. I will show you. If this is the channel bottom, this is how the water surface is. And the energy line is always straight like this. This is energy line. This is water surface. This is channel bottom. Suppose this is the section. If I draw the plan, this is the channel width here, section 1, section 2. Same is the section here. This is section 1, section 2, section 2. So here it is B1, here it is B2. Because reduction, it is plan, reduction in width of channel, right? Then here it is flow is like this, flow is like this. This is Y1, right? He mentioned actually a rectangular channel 2.5-meter wide. So B1 is equal to 2.5-meter wide. Okay, and the flow is Q is equal to 2.75 meter cube per second, that is second data, and Y1 is equal to zero point 0.9 meters. This is what he has given. A contraction in the channel width is proposed at a certain section. Find the smallest allowable contracted width. So the smallest contracted width means actually the smallest contracted width is at critical flow. This is one you should know it. This is crux. That means what? Here Y2 should be equal to YC. And this is V1 squared by 2G. This is VC squared by 2G. So at this section B2, Y is equal to YC. That is what you should understand. Then that is up to that only, up to that critical flow only, you can reduce the width. So here flow is general, subcritical flow. So then as you are basically contracting the section, as you are reducing the width, what will happen? The velocity increases and at certain depth, it will reach to critical depth. So that is if suppose you reduce beyond critical depth, beyond this B2, what will happen is Y1 will change. So that's why we can maximum reduction is possible up to critical depth. That you should remember, right? So if you know that condition, now I will take you what is the thing, how to go about it. So first let us take upstream conditions. Upstream. I will go for the first upstream, right? Upstream means what? Section 1. Section 1, what I can calculate? What is V1? V1 is equal to, how to calculate actually? Q by A1. Q by A1 means what? Q is equal to, that fellow has given 2.75 divided by A1 is B1 Y1. So that is equal to 2.75 divided by B1 is equal to the B1, what, how much they have given? B1 is equal to 2.5 into depth is zero point 0.9. So if you calculate V1, that will be 1.222 meters per second. This is the first calculation. Once that is over, what is F1? That means incoming flow Froude number. It is V1 by root GY1. So it is equal to 1.222 divided by square root of 9.81 into Y1 is how much? 0.9. So that is equal to, you are going to get 0.411. So that means it is less than 1. Therefore, what type of flow it is? Subcritical flow. This is the first thing. Then what is E1 is equal to Y1 plus V1 squared by 2G. So what is Y1? 0.9 plus what is V1? 1.222 squared by 2 into 9.81. So that is equal to how much? 0.9761. This is the first thing. Right? Now I will apply the energy equation. According to energy equation, energy remains same. That means E1 is equal to E2. That is first thing. So if that is the case, we wish to have maximum reduction in width at section 2. That means at section 2 flow is critical. So for critical flow, E2 is equal to E minimum, right? This is the next thing. Then if such a case actually that E1 is equal to E minimum. This is comparing section 1 and section 2. Therefore, what is E minimum? E minimum is equal to already E1 that is calculated. What is E1 plus E1 is equal to 0.9761 meters. So this is the next. So E minimum, if I know from E minimum, can you calculate what is YC? We know actually E minimum is equal to 3 by 2 YC. Therefore, YC is equal to 2 by 3 into E minimum. So it is 2 by 3 into 0.9761, which is equal to 0.6508 meters. That is over. YC also we got. When once YC we got it actually, you also know that what is YC? YC is Q2 square because section 2. Q2 square by 2G whole to the power of 1 by 3. So 0.6508 is equal to Q2 square divided by 2 into 9.81. Hence, what is y Q2? What is Q2? So, if you calculate what is Q2, Q2 is equal to, it will be 1.644 meter cube per second per meter width. So, therefore, if you then calculate what is the P2 is equal to, it is nothing but Q by Q2. Already Q is given to us, it is 2.75. Q2 is 1.644. So what is B2 is equal to, if I calculate it comes to 1.672 meters. So that means the minimum contraction, the width can be contracted up to 1.672. Kindly remember, note that if you reduce beyond this, beyond this 1.672 meters, the upstream depth changes. This is the second problem. So we have done two problems. One is covering the hump problem. Second one is covering the base, the reduction in width problem. The last problem I will do taking into account problem 3. Both the things actually, both reduction in width and hump together in one problem. A 3.6 meter wide rectangular channel carries water at a depth of 1.8 meters. In order to measure the discharge, purpose is this. In order to measure the discharge, the channel width is reduced. Number one, to 2.4 meters and a hump of zero point 0.3 meters is provided in the bottom. Calculate the discharge if the water surface in the contracted section drops by 0.15 meters. Assume no losses. So this problem actually two are there. One is if I take this is the thing, this is the hump, right? Then this is the water surface. This is the problem, right? Whereas the other one this is the section. So this is water surface. I can draw energy line also, right? If I take this as section 1 and this as section 2. So here it is y1, right? This here it is y2, right? And he has given this is basically he himself has given some basically 0.15 meters, whereas this is v1 squared by 2g, whereas this is v2 squared by 2g. This is the line. So this is energy line. This is water surface. Right? And this is channel bottom. This is hump. This is the thing. Suppose if I go for this next one, plan, this is the thing. This is how. So this is section 1. This is section 2. Here it is B1. Here it is B2. So this is the thing you should remember. This is plan. Both are there in the same problem. So now if I apply energy equation, applying energy equation, what I will write y1 plus v1 squared by 2g is equal to delta z plus y2 plus v2 squared by 2g. This is what I can write. Next, again, as there is no loss of energy, right? v1 squared by 2g plus 0.15 is equal to v2 squared by 2g, or the difference of velocity heads is 1.15. That is better to write v2 squared by 2g minus v1 squared by 2g is equal to 0.15. That is what he has given. So now what I will do, for example, I take the energy equation and see what I can do. So y1 plus v1 squared by 2g is equal to, that is hump height is how much, delta z, I don't know. Then it is y2, then it is v2 squared by 2g. v1 is y1 is known, right? y2 is unknown. Then v1 v2 both are unknowns. Then how to go about it, right? How to go about it? Delta z is given, so y1 is equal to, he has given it how much, y1 is equal to 1.8. So that is over. What is delta z given actually? Hump height is given actually how much, zero point 0.3. So that is also over. So this is over, this is over. Now these two are there. But I know what is v2 squared by 2g minus v1 squared by 2g is equal to 0.15. Right? But this is from this you can see. So therefore, if I substitute like that, what we will get, we will see y1 is equal to delta z plus y2 plus v2 squared by 2g minus v1 squared by 2g. So it is delta z, y1 is equal to how much, 1.8. Delta z is how much, 0.3, plus y2 is unknown, plus this difference is 0.15. So therefore y2 is equal to how much? y2 is equal to 1.35 meters. This is the solution. The next one is what he has asked is, what is Q? This is next. So in order to do the Q, my option is only one. Option is what? Basically V2 squared by 2G minus V1 squared by 2G is equal to 0.15. That is the only thing that I have in my equation. So therefore, I will write what is V2. V2 is equal to Q by A2. Right? What is Q? I don't know. Q by A2 is what? Well, it is B2 Y2. Right? So that means it is Q by B2 is how much he has given. B2 in the problem he has given 2.4 into Y2 how much we calculated 1.35. So this is one answer. V2 we got it. Then what is V1 is equal to Q by A1. So if I do it V1, what is V1? V1 is equal to Q by A1 means Q by B1 Y1. What is Q by B1 Y1? B1 is how much he has given? 3.6 into The depth of flow is 1.8. So this is, now you write what is V2 squared by 2G. V2 squared by 2G is equal to Q by 2.4 into 1.35 whole square by 2 into 9.81. What is V1 squared by 2G? Q by 3.6 into 1.8 whole square by 2 into 9.81. So now you write V2 square by 2G minus V1 square by 2G is equal to Q Q square by, what is that actually? 2.4 into how much? 1.35. 1.35 whole square minus Q square by 3.6 into 1.8 whole square into 1 by 2 into 9.81. So if you solve all this all equation is equal to 0.15. So therefore, if you do it, you will get like this: Q square into 1 by 205.96 minus 1 by 823.85. So automatically this becomes 0.15. Therefore, Q is equal to 6.418 meter per cube per second. So this is another problem. So with this, we have solved three problems. One is first transition, a floor with a raised floor. Second one is a floor with a hump that we have solved. The second problem which you have solved is a width problem, reduction in width problem. And third is both hump and reduction in width. So these are all the problems in this. With this, the critical flow topic is complete. So the entire critical flow chapter I have done in 5 lectures. The first lecture is devoted to specific energy curve. The second lecture is devoted to then critical depth, critical flow equations, then subcritical flow, supercritical flow. That is second lecture. Third lecture is some problems on specific energy, critical depth. And fourth lecture is transitions. And the fifth lecture is problems on transitions. So these are the 5 lectures. With this, the entire specific energy topic is complete. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.